Hello, my name is Sjo Kremers, and I'm a research intern at CWI and master student at TU Delft, both in the Netherlands. And with this, I'll be presenting the work on approximating Shapley value in energy communities with shared assets, which was done under the supervision of Dr. Valentin Robu, and along with our colleagues Dan, Titus, Kawin, and Sonam from TU Delft and Heriot-Watt University. Currently, many governments are supporting more and more the use of renewable energy sources, such as solar panels and wind turbine, to the public by giving them financial incentives. And because of this, many households are not only energy consumers, but also producers. And we call these households prosumers. Since these renewable sources are often not dispatchable in terms of energy generation, households are often equipped with a battery, which gives more flexibility to their energy usage. Now, if you have excess energy and the battery is also fully charged, then you can sell the energy to the utility grid. But normally the price they buy your energy is very small that it is almost negligible. On the other hand, if your demand is not met by the energy sources, then you have to buy the energy from the grid, but the buying price is normally much higher. So there's clearly a financial benefit to interact with the neighbors so that you can reduce this redundancy and use as much of the energy generated within the community. Currently, there are two main approaches to this. One is peer-to-peer energy trading, where the neighbor prosumers buy and sell energy with each other directly. Second is forming energy community, which is our focus in this study. In an energy community, group of households invest in assets like wind turbine and battery together. Here, the whole community acts as a single entity and interact with the grid. In this case, the energy generation capacity and the battery usage is optimized for the whole community, so there are less wasted energy. Because of this, the total cost of the energy community is lower than the sum of prosumers with individually owned assets. This sounds great, but it brings to an important question. How do you redistribute the total community cost to individual households in a fair manner? Many studies have looked at the Shapley value, but the main problem is that it has exponential time complexity, and so it can only be used for small communities. Previous studies have also looked to approximate the Shapley values, but it is not very clear how well they approximate for large communities, because again, Shapley value is intractable in such cases. So in this study, we introduce a new cost redistribution method that is both time efficient and aimed to approximate the Shapley value well and compare the performances with existing methods. And to compare the performances, we propose a method to compute the Shapley value of larger community in a more tractable manner, provided that the agents are grouped into limited number of demand profiles. The true Shapley value can then be benchmarked as the ground truth to compare the redistribution method. Finally, we perform experiments on a total of 3 methods, including the newly proposed one, in a large setting with up to 200 agents in the community and energy generation and demand data of every half hour for a whole year. So in this study, a community consists of prosumers that have half-hourly demand for a year, a community battery, and a community wind turbine, which also have half-hourly energy generation for a year. The total energy cost of the community is derived from 3 separate costs. One is the cost of importing energy from the grid, which is dependent on the consumption behavior of prosumers and energy generation. The other 2 costs are wind turbine and the battery, which are both dependent on the number of consumers and increases linearly with the community size. And this cost can be calculated for any subset of the agents in the community, and it can be seen as a cost function. Now that the cost function is defined, we can move on to the redistribution method, but first I'll go over the Shapley value formula. Here you can see the Shapley value of agent I in the community. Here it goes through every possible subset of agents in the community and compute the marginal contribution. Marginal contribution of the agent to the subcoalition is how much this agent adds to the cost by joining the subcoalition. This marginal contribution is then multiplied by the relative frequency of the subcoalition. So this resulting Shapley value is the average marginal contribution of this agent in the community. Shapley value can also be expressed through concept of stratum, which is an important concept in our methods. A stratum is all possible subcoalition that can be formed with certain size. So stratum 5 mean all subset of Asians in the community that can be formed with a size of 5 Asians. In this equation, again, it computes the marginal contribution, but takes the expected marginal contribution of each stratum, and then the average of these marginal contribution is equal to the Shapley value. From both of the equations, you can see that it has to go through every possible subset of presumers in the community. So it has exponential runtime in the community size and becomes intractable very quickly as the community size grows. So now we go on the first redistribution method, which is called the last marginal contribution. In this method, the cost of the presumer is the marginal contribution of the rest of the community. We also need to normalize the redistributed cost to make sure the sum equals the total cost of the whole community, and that's it. It is a very simple method, but also very efficient for large communities. The second one is the newly proposed method by us, and we take a step further from the previous method. In this method, we imagine that when calculating the cost of a presumer, the rest of the community have the same demand for the whole year, which is the average demands for the rest of the community. Then for the presumer, we compute the marginal contribution of every stratum with these average presumers. The previous method only looked at the last stratum, but this method aimed to approximate the expected marginal contribution for every stratum. So that's why we believe this method would approximate the Shapley value better, and we name it stratify expected values. We also need to normalize the redistributed cost to make sure the sum is total cost of the community. Finally, we also looked at the performance of the state-of-the-art random sampling method by O'Brien et al. This method is different from the two previous ones, that it is not deterministic and it has randomness to it. So given the number of samples predetermined by the user, which was set to 1,000 samples per presumers in this study, this method samples marginal contribution randomly from each stratum. And it uses reinforcement learning technique to adjust the number of samples given to the strata while running. So this method can approximate the Shapley value quite well, but the number of samples required to approximate can grow fast as the community size increases. So it has the largest time complexity of the three methods. Now that we have the method to redistribute costs, we need a way to compare how close they are to the true Shapley values. As I said before, it is impossible to compute for large community size if the presumer is unique. But if the presumers are grouped like here, where the presumers in the class have the same exact demand, then the two cases here both have the same community sizes, but the true Shapley value can be computed much more efficiently in the second case. First of all, you only need to compute the Shapley value once per class. And also, the number of unique subcoalition that can be formed is less than the original case, because substituting any agents in the same class won't affect the cost of the subcoalition. So overall, this is a special case, but allows to compute the exact Shapley value for large community, and it can be used as the ground truth to compare the redistribution methods. For the experiment, we use real consumer data of 200 households and corresponding wind turbine energy data from the UK. We then grouped the consumption behavior during the winter days of these presumers using k-mean clustering and selected 3 classes that had distinct behaviors. Here you can see the average daily consumption of what we called work at office, work from home, and night owl classes. For the experiments, we created communities using these classes. Here you can see the result of the experiment. On the left figure I'm presenting here, we keep the proportion of the different type constant and vary the number of agents in the community. The community was made up of 70% work at office, 20% work from home, and 10% night owl classes. The x-axis shows the community size, and y-axis shows the performance of the method, and closer to 0 meaning approximate the Shapley value is better. The blue line is the result of the last marginal contribution method. The red one is the newly proposed stratify expected values, and green line is the state-of-the-art adaptive sampling method. You can see that all the methods perform very well for large community size, having only 0.1% difference to the true Shapley value. Still, the stratified expected value outperformed the simpler marginal contribution method and have similar error value to the adaptive sampling method while having a smaller time complexity. The result on the right is when the community is kept to a constant size, and in this case 100 agents, but we change the proportions of two classes. So more on the left of the figure means the majority is work at office class, and the more you go towards the right, the majority becomes work from home class. Here you can see that the error is quite small for all cases, being less than 0.2% error, since the community is quite large. But still, the stratified expected values and adaptive sampling outperforms the last marginal contribution method. And in this experiment, there is quite an overlap between the stratified expected values and adaptive sampling method. A potential advantage of deterministic methods like the marginal contribution and the stratified expected values over random sampling methods is that every time you run the algorithm in a certain setting, it will return the same results, which is not the case with random sampling methods. This also guarantees that the consumers with same exact demand will be redistributed the same cost, and it is easier for consumers to verify how the cost was calculated, which increases the trust and perceived fairness of the system. Overall, our finding shows our newly proposed method provides a good Shapley approximation while having small time complexity. We're also currently looking at larger data set containing demands of over 5,000 households and testing with larger number of classes and more scenarios to provide more confidence with the results. Thank you very much for listening to the presentation.